before we get going, let's hit a question about Blackboard. The reason I'm doing this is to make sure that what I think is out there is accurate. Okay? Sometimes Blackboard is an unreliable package, so let's see. I thought I clicked this, but nothing happened. So sorry, this will take just a couple minutes to do, maybe or more if the system doesn't. Well, it acts like it's going to open and then it doesn't. So let me try it one more time. It'll probably open 3 times in a row now. Still nothing. Oh, but it's going to try a little something else. It's doing more than it did before. So maybe it'll open this time. Maybe. Or maybe it'll sit there and spin. Okay, still nothing. Oh, this is discouraging. Let's try it one more time. Still see nothing. So, there we go. All right. Oh, there, it's open the second time. Okay. So Google is, there we go. I don't know. What that's about, but I'll say yes. Okay. So let's go to Blackboard. Boy, it's slow. All right. Awfully slow. Waiting for Blackboard. That's half my life, is waiting for Blackboard. Okay. Still waiting for Blackboard. Processing request. Okay, here we come. All right, now I've got probably a few more courses than you do, so let's scroll down to 126, Fall 1920. All right, once you get here, just there's a little bit of review. This is this course of the thing. The syllabus and book information is in this tab here. The locator card is in that tab. Go down here to handouts, PowerPoints, and more. I don't know if you can see it because of that. Okay, so click on that. Okay, and there's the research paper instructions. There's all the PowerPoints in static form. All right, and there's the Math 126 YouTube videos. You see that? Okay, click on that. Now, these at the top are from previous terms. Don't worry about those. Scroll down to the bottom until you see the one that says syllabus. Okay, that's where this term began, and the The last one we did was 7.5 through 6. And that took us right to where we are now. Click on that and it should come up what we did last time. Okay. Does that get you there? Have you done this and still can't get it? Okay, good. So that's how to get there. All right. Dawson's here. So I'm not going to sign in or anything else while you can get on from there. So I'm going to close YouTube, close Blackboard, close that, and this is where we begin today. So I'll go and open it from current slide. I'll open it from current slide. There we are. Before we get going, let me go over these few announcements. Today is the 23rd of September, and tomorrow our volleyball team will be hosting Coastal Alabama East. Okay, I'm not exactly sure what that is, but that'll be a match at 5:30 on the Birmingham West Campus in the Arthur Schwartz Fine Arts Building, which is also the gym. That's tomorrow, okay? Tuesday the 24th. I'll read you the rest of these as they get closer. And again, I've announced before the College Scholars Bowl. The College Scholars Bowl team is currently recruiting players with knowledge of any subject, including history, literature, science, music, current events, mythology, and mathematics. So, what's that? If athletics, that would be under current events, probably. So, I would include that. Today, as I said, was the 23rd. Today is the last day they will have the exhibition over in the Birmingham West Campus Library of the Darkness into Life, the high school, the Alabama Holocaust survivors through photography and art. Should be a great exhibition. I got to at least glance at it on Friday. I didn't get to go in and take a thorough look because I was swamped doing other things. So anyway, it's still there today, but today's the last day. And the NASA's Community College Aerospace Scholars Program will be accepting applications through October 16th. It's just a little over between 2 and 3 weeks away. So don't delay. Go on and check it out. I have a bunch of websites you can go to find out more about it. It's a great program. Speak with any of the students who have participated, including Fred, who's in this class, and you'll find out it's a really good program. All right. Okay. Any questions on anything we've done up till now? Okay. We're in, Chapter 7, Applications of Integration. We're in 7.6, Moments, Centers of Mass, and Centroids. Okay. These are all related, but we're going to talk now about how to do this. Okay. It says, find the mass in slugs. This is so ridiculous to have this in the calculus book, of an object whose weight at sea level is 1 pound. This has nothing to do with calculus. So let's just do it quickly. Anyone know how to determine this? Let me get my pen set up. This will be more physics than it is calculus by a long shot. Find the mass. So we're looking for mass. That's the unknown here. Of an object whose weight, and I don't remember if this book had, it didn't. So I'll use one of the many abbreviations for weight. One is F sub W, the force due to weight. the pulling down of the Earth's gravitational field. This is what we know. This is 1 pound. Now, do we also know a formula that relates weight to mass? Please say yes.
Mass equals force divided by acceleration.
Okay. That is true. It comes from force is equal to mass times acceleration, and the acceleration due to weight is the acceleration due to gravity. So that would be mg. Okay? We are looking for mass. We know g, or I hope you do, and we've just written down what the weight was. So what Patrick just did was do mass is equal to the force due to weight, or just the weight, divided by g. Well, this weight is 1 pound, but rather than writing pound as pounds, okay, we'll write it in its fundamental units, which you never do, but we're going to do it now. That's a slug foot per second squared. Okay? And we're going to divide that by the acceleration due to gravity. Now, which system are we dealing with here? The SI system, which is metric, or the U.S. customary system? We're talking about. Say again? I can't hear.
English.
Yeah, the English or the U.S. customary, right. And what is the acceleration due to gravity in the U.S. customary system? No, that is an SI. It's 9.8 meters per second squared. What is it in the U.S. customary or English or British system? Anyone know that one? If you look in your, well, let's see, is it in the book? It ought to be. I would have thought so somewhere here. But no, they haven't. Sorry. G, as you just said, in the SI system is 9.8. Sometimes people use 9.80 meters per second squared. In the U.S. customary system, I'm just going to put U.S., it is 32, some people use 32.2 feet per second squared. Okay? So you're using U.S. here. So this will be divided by 32 feet per second squared. Notice how the units cancel out, and this leaves the slugs. So 1 divided by 32. Anyone want to punch that in and see what you get? $3,125, yeah. Anyone got it?
0.03125.
125. Okay. And that would be in slugs. No one ever uses slugs, okay? They don't even have an abbreviation for it. It's just not used. We usually talk about pounds in the U.S. customary system. We usually don't talk about mass at all. Okay? It says because many applications involving mass occur on Earth's surface, this amount of mass is often called a pound mass. That's just a shorthand to keep from using slugs. All right. Let's clear this out of the way, and we'll see how they did it, which is fairly. Use 32 feet per second, or 32 feet per second squared as a shorthand as the acceleration due to gravity. The mass is then the weight divided by the acceleration due to gravity. 1 pound divided by 32 feet per second squared. That's a lot easier than writing feet per second. And that gives you 0.03125 slugs rather than writing pound for the fruit per second. There I would write slug, even though no one uses it. And they say this is often called they wrote it slug there. Because many blah, blah, just what I just read. That amount of mass is referred to as a pound mass, which is a very small number of slugs. A slug is a significantly large mass, okay? We just don't use it. We would say that's 1 pound mass, and pretty big different number, okay? All right, then let's move on to center of mass of a one-dimensional system. Okay, we're still approaching the calculus part, but not quite there yet. We'll now consider two types of moments of mass. The moment about a point, and then later the moment about a line. Okay? To define these two moments, consider an idealized situation in which a mass m is concentrated at a given point. If x is the distance between that point mass and another point p, then the moment of this mass m about that point p, which is a different point, x units away, the moment about that is m times x. So a moment is a mass times a displacement. A mass times a displacement, think gram centimeter or kilogram meter or something like that. X is the length of what they call the moment arm, which is the distance that mass is from whatever your reference point is. Okay? That is your moment arm, is another way to look at it. The concept of a moment can be demonstrated simply by a seesaw. Okay? If you had this situation here where this 20 kilogram kid was sitting here and the 30 kilogram kid was sitting there. They're each 2 meters from the point in question. What's going to happen to the seesaw?
Tilt up where the lighter kid is at.
Yeah. The heavy kid, this always happened to me in primary school because I was the heaviest one in my class, tilted that way. We had a very small school. I was big for my age until I got to 7th or 8th grade, and then everybody passed me. Okay. So, anyway, that's, you're absolutely right. That would do. Why? Because there's a greater moment here. 30 times 2 is 60 kilogram meters this way, 40 kilogram meters this way, greater moment there, so it's going to twist in that direction. Seesaw will balance when the left and the right moments are equal. They're not in this case, so it will not go. From experience, you know that the seesaw will begin to rotate clockwise, moving the larger child down and kicking the 20 kilogram kid up in the air. Oh, I'm sorry, I didn't read this. Child of mass 20 kilograms sits 2 meters to the left of the fulcrum P, and an older child, no, he was older, of mass 30 kilograms sits 2 meters to the right of P, and we know it's going to rotate in the clockwise direction because there's a greater moment on the right hand side than on the left. Now, how could you get it to balance?
You could possibly scoot one of them up.
Okay, which one?
The lighter kid, one on the left.
Okay, and you scoot it which way?
Closer to the bolt.
Ooh, that would decrease the moment arm. What you need to do is scoot him back, increasing that, and if that wasn't enough, you don't want him falling off, then scoot this one forward to decrease his moment arm, because mass times displacement equals mass times displacement. So if you can increase this displacement and or decrease that one until the two are equal. Okay, so let's say you had 20 times 2.5, if you could, I don't know if there's that much board left, that would be 50 kilogram meters. That would still be 60, so you scoot him forward until you can get 2.5 out of this, 30 times some shorter distance there. That would do it. So you see, that's how you get them to balance. Know your math. You're both pre-engineers? Okay. you'll be hitting these kind of problems in statics and dynamics. I guess they still teach those with those names. Those will be two of the early courses you'll take when you go junior year to a four-year school. Somewhere in your first couple terms, you'll take statics and dynamics. You won't have to take it, but you may take something similar to it. I don't know. I doubt it. Okay? Now, that rotation occurs because the moment produced by the child on the left is less than the moment produced by the child on the right. We already said this. The left moment was 40 kilogram meters, and the right moment was 60 kilogram meters. So it's going to twist that way. To balance the seesaw, the two moments must equal. For example, if the larger child, the 60 to 30 kilogram child, moved to a position 4/3 of a meter from the fulcrum, rather than 2 meters, that's a meter and a third, then the seesaw would balance because 4/3 times 30, 30 will go into, 3 will go into 30 10 times, and 10 times 4 would be 40 kilogram meters. So just moving that one in, that would make it work. Because each child would then produce a moment of 40 kilogram meters. Okay? Or, as you said, the other one could move in the opposite direction until you get them to balance. Or do some of both. All right, you can introduce a coordinate line on which the origin corresponds to the fulcrum, and then you got it sort of knocked here, okay? Several point masses are located on the x-axis, okay? The measure of the tendency of this system to rotate about the origin is the moment about the origin, okay? We were saying the fulcrum, before that, point P, now we're saying it's about the origin. It's defined as the sum of the end products, m sub I times x sub I, where n in this case happens to be 5, it looks like. Okay? So if your first mass m1 is x1 units away, and this appears to be a negative, right? Plus m2 times x2, which also appears to be negative, okay? Plus m3 times x3, which appears to be positive, plus, and then whatever the next one, we're always saying m4 times this, plus m5 times that. Depending on what the masses are, you'll see what the writing arm is, okay? So if this m1x1 plus m2x2 plus m3x2 plus, if all those add to 0, then the system's in equilibrium. For that to be, masses are never negative, by the way. Show me something with a negative mass. Can't do it, okay? It's always got a positive mass. The distance can be negative, because these are left of 0 and these are right of 0. But if you can make that equal 0, then the system's in equilibrium. That's statics, okay? When they're not in equilibrium, that's dynamics, okay? That's a really oversimplified view of what the two courses are, but that's what you're dealing with. Okay. Any questions on that? All right. The moment about the origin is denoted by m sub O for origin, or 0 for 0, 0, or whatever, and can be written as the moment is m1 x1 plus m2 x2 plus m3 up to mn x sub n. Okay? If that moment is 0, the system is in equilibrium. If it's not 0, it's tilted one way or another. If it's negative, it's tilted this way. Positive, it's tilted that way. All right. Make sense? All right. Okay, here, we're still here. For a system that is not in equilibrium, the center of mass is defined as the point x bar, okay? It may have been in your past, x bar represented the average of x. In a little bit of a sense, it's kind of like an average, but it's not quite the average x, okay? is the center of mass, x bar, okay, at which the fulcrum could be relocated to obtain equilibrium. That's wherever the center of mass is, that would give you equilibrium. If the system were translated x bar units, either right or left, whatever it took, then each coordinate x of I would become x of I minus x bar, whatever the x bar. You see, here you have to know the x bar to know how far to move it. And because the moment of the translated system is 0, you have that all these are equal to 0. This is m, the summation of all your m sub I times x sub i's, except it's now not x sub I, it's x sub I minus x bar. So if x bar is to the right, that's going to be a negative number. If x bar is to the left, this will be a positive number. In other words, if the x sub I is to the left, it's less than x bar, so that's going to be your negative number. All the ones that x sub I are to the right, those will be positive numbers. That's how you balance things out. But notice here, you can break this down because this is just a simple difference here. It's m sub I x sub I, okay, minus m sub I x sub r. X bar, not sub bar, x bar. Okay? Now, if you solve for this x bar, that means add this to the other side and then divide by your sum of your m sub i's. So you get this expression here. Get this one. This is how you find that center of mass. The moment of the system about the origin, those are all of our moments, added up, about the origin, this is about the origin, divided by the, and what is that? X of r is a fixed number, that's why you can pull it out of the summation, and this is just the sum of all your mass, the total mass of the system. So this is how you find your x bar. The sum of all your moments, which is your masses times the displacement, divided by the total mass. And that gives you your displacement. Yeah.
So the x bar, is that the equilibrium?
Equilibrium position,
What's
exactly.
the difference
We
between
call it the center of mass. Huh?
What's the difference between equilibrium and average?
Okay. If all the masses were the same, it would be the average. But you see, you don't require that. These could be varying masses. But if all the masses were the same, it's going to be the same as the average. Okay? So that would be the difference. That's how they're related, but it's not reality because most of the time they're not all the same. When all this m sub I, x sub I, when all these added up is equal to 0, the system is in equilibrium, which we've already said a couple of times. So then your x sub r would be right where your origin would be. So this is actually saying the same thing we did at the very beginning. Now, this is sort of a dumb example of this, but I never saw it, but I heard it many times. When I was in probably junior high, I believe it was, I heard about this guy. I'd heard his name before. His name was Paul Anderson. He was an Olympic weightlifter. He won the gold medal for the U.S. in the heavyweight division. And he lived the next county south from the county I was in when I was in junior high, in Georgia. He lived in Millen, Georgia, if I'm not mistaken. That's my memory anyway. And he was also a really fine, quality person. And he would go around giving talks, inspirational talks to kids. And he would, this is what they claimed. They would set up a platform and have all the kids these would be elementary age kids, get up on the platform, and he would get underneath the platform with the entire class of kids on it and lift the platform. He was strong. And, he talked about the center of mass, having your life centered, and then you can pretty much handle things when it's all centered. Yeah, he was a good dude, a really good dude. I never got to hear him, but I heard about him. When I was in grammar school age, he probably hadn't gotten the gold medal yet, so it was a little before my time. But anyway, I heard that he did that. Pretty impressive. If you're under the center of mass, you can move a lot of stuff. Okay. Archimedes said something close to it, but not quite there. He said, give me a long enough I can't remember what he called it. A long enough pole, basically, and a fulcrum to put it on, and I can move the world. Okay? Of course, there wouldn't be a place to put it, but he did. And the same thing, that if you had a long enough riding arm, just your mass would be able to lift the world. That would be an awfully long one, and you'd have to have something pretty solid to put it on. But Archimedes understood that. For a system that is not in equilibrium, the center of mass is defined at the point. Wait, we've already done that. I thought I had turned the page here. Okay, so here's our definition of center of mass. Okay. By the way, this is top of page 496. Moment in the center of mass, one-dimensional system. We're only dealing in one dimension here. Let the point masses M1, M2, up to M sub n be located at these positions, x of 1, x of 2, up to x of n. The moment about the origin is this M sub 0, we've already done this, is M sub 1 times x of 1 plus M sub 2 times x of 2 plus blah, 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 up to M sub n times x of n. Now, if all these x's are positive, that moment's going to be very positive. If all the x's were negative, there would be a very negative moment about the origin. If some are positive and some are negative, they're going to tend to balance a little bit, but they may not balance out completely. Okay? The center of mass, on the other hand, is the position, x bar, where the center of mass, m sub o, whatever this happened to be, divided by m, that would be the value of that. So if this is a very negative, like I said, all these x's over here, your center of mass is going to be negative. Somewhere in the middle of those, not in this exact middle, but somewhere in the middle, that would then be your center of mass. Okay? If all these were positive, then it's somewhere over here. Kind of in the middle of them, okay? In the midst of them, I guess is the better thing to say, with some on the left and some on the right. If these are mixed up here, then you're already getting close, and you just adjust your x bar, negative or positive, until you make that. If this is slightly positive, this will be a slightly positive mass here. All right, center of mass. If this is slightly negative, this will be slightly negative. Now this m here is the sum of all the masses, the total mass of the system. Okay. Now we're talking now about individual discrete masses on the x-axis, basically. So here's example 2. Find the center of mass of the linear system, meaning it's along a straight line, shown in this figure. You do it. What would be your m sub 0, moment about the origin? Give it to me. The number inside is the mass, and the number at the bottom is the displacement. So what would that be? 10 times a negative 5. Plus 15 times 0. I think I can do that one. Okay. Ah, the other swimmer finally got here. Okay. Josh is here. Okay. Say again? Plus 5 times 4. Plus 10 times 7. Okay. What does that add to? Negative 50 plus 20 plus 70. Say again?
So from that, we'll have
40. Perfect. Okay? That's your m sub 0. Plus 0. I got it. Okay. Got it. Okay? Now, what else do we need to do to get our center of mass? Total mass, M. What's your total mass? Anybody? 40. Okay. So what's your X bar? 1. So if you put the fulcrum right here, X bar is a length measurement, so you put your bar there, and then you'd be fine. Let's see if that indeed works. This would be 10 times, now you're minus 6 from there. This is minus 60, and this would be a minus 15, because now you're 1 to the left. Minus 60 minus 15 is minus 75, right? Okay. You're 6 to the left of this place, right? So this would be 6 times, minus 6 times 10 would be minus 60. And your 1 to the left of this would be minus 1 times 15 is minus 15. Minus 60 plus minus 15 is not that hard. Minus 75. All right. Let's go to the right. You're 3 units to the right here. 3 times 5 is 15. And you're 1, 2, 3, 4, 5, 6 units to the right here. 60. 16 plus 60 is plus 75. So yes, that's your center of mass. 1. Okay. Now, does it seem right that this one has more work? Okay. Have you ever heard of things? I know they do it in Blackboard some. I never trust Blackboard to do it right, based on some of the things we were looking at earlier in Blackboard. But they have weighted averages. For instance, you're in a class and this paper is worth more than this paper is worth, or this test is worth more than the quiz, or something like that. If they weight it, that's what you're doing. This is weighted more than that, so you get more points out of it, even though it's a 10 rather than a 15, because that's a lower weight. That has a weight of 1, this has a weight of 60, like 6. So anyway, so sure enough, that worked. Let's see how the book did it. Any questions before I erase this? Linear systems like this are pretty easy to check, okay? So the moment by the origin, just like we said, is m sub 0, 0 standing either for O for the origin or 0 for 0, 0, whichever it is. It looks like a 0 to me. But it's m1x1 plus m2x3, blah, blah, blah. Add all those up, 10 times minus 5 plus 15 times 0 plus 5 times 4 plus 10 times 7 is negative 50 plus 20 plus 70 equal 40. Your total mass of the system, 10 plus 15 plus 5 plus 10, is 40. And the center of mass would then be your moment divided by your mass, which is 1. Note that the point masses will be in equilibrium when the fulcrum is located at x equal 1, and we just verified that. Rather than defining a moment of mass, you could define a moment of a force rather than a mass. In this context, the center of mass is called the center of gravity. And that's really what I was talking about with Paul Anderson getting under the center of gravity. But guess what? On the surface of the Earth, mass and weight due to force, they're related by a constant. So they're multiples of each other. Consider a system of point masses, M1, M2, M3 up to M sub n, and located at x of 1, x of 2 up to x of n, Then because the force is the mass times acceleration, then you have the total force of the system is M1A times plus M2A plus M3A plus M4 up to M sub n times A, which is all your total mass multiplied by the acceleration. Okay? The torque, new word here, torque about the origin is your M1A x1 plus M1A x2 plus all the way up to M sub n A x n, which is just your moment times your acceleration. The center of gravity is then that torque divided by the total force, and that also comes out being x bar, because the acceleration on the top is the same as the acceleration on the bottom. Now the reason for that, if this is a system and the entire system is accelerating, which is what's implied here, then all the masses are moving at the same acceleration. Now if it wasn't, all bets are off. That's a chaotic system. But if they're all moving with the same acceleration, therefore the A's cancel out in the numerator and the denominator, and you get the same center of mass. So the center of gravity and the center of mass have the same location. So therefore it doesn't really matter which one you're talking about. Now in your engineering, and Josh, are you also a pre-engineer? Okay. When you're taking your statics and dynamics, they will be talking a lot more probably about force torques than they will, well, I think they talk about both of them, so be ready for them. But they're really defined very close to the same thing. One's dealing with forces, one's dealing with masses. Now, what if we're dealing with a two-dimensional system? You have not just movement along or distribution of masses along a line, but you have them in a plane. Okay? Here's what we're dealing with it. You can extend the concept of moment to two dimensions by considering a system of masses located on the xy plane at points x1, y1, x2, y2, up to xn, y sub n. Okay? So these are various points in the plane. In this case, your M1, the M's are always positive, by the way, but your x sub 1 is negative and your y sub 1 is negative. Here, your M sub 2, the x sub 1 is positive, and the M, of course, M is positive. Your y sub 2 is positive. Down here, here's the one that is represented as the M sub n. The mass is always positive, but x sub n positive, y sub n happens to be negative. So you could have any combination of these, as many as you wanted, but a finite number for now. Okay? Rather than defining a single moment with respect to the origin, that would be tough here. Two moments are defined, one with respect to the x-axis and one with respect to the y-axis. Okay? So, in a two-dimensional system, there's a moment about the y-axis and a moment about the x-axis. Okay. And here's the rules for this one. Let the point masses M1, M2, up to M sub n, all positive, remember, be located at positions x sub 1, y sub 1, x sub 2, y sub 2, up to x sub n, y sub n. These x's can be either positive or negative. The y's can be either positive or negative. And the x's and y's are completely independent of each other, so one can be headed in one direction, one the other direction. It doesn't matter. So, the moment about the y-axis, only about the y-axis, okay? That's the mass times the distance from the y-axis. What's the distance from the y-axis? Distance from the y-axis. Doesn't matter where it is this way, the distance from the y-axis is your x sub 1, x sub 2. So the M sub y, moment about the y-axis, is your moments, the sum of your moments from the y-axis. m sub 1 times x sub 1 plus m sub 2 times x up to m sub n times x sub n. Remember, the m's are always positive, but the x's can be either positive or negative. Doesn't matter. The moment about the x-axis would then be simply m sub 1 x sub 1 plus m sub 2 x 2 plus up to m sub n x n. In this respect, I find referring to them as moments because they're always the opposite. This is sub y with respect to y, it's the x's with respect to x's. The y's, I usually like to forget about the moments. I just like to use these. They are the moments. Forget about the nomenclature. The center of mass, x bar, y bar, or also called the center of gravity, okay, is x sub bar would be, x sub bar is m sub y. Why m sub y? That's where your x's were located, divided by your total mass. M is the total mass again, where your y bar is your m sub y's. Some of your moments about the x-axis, but your m sub I, y sub i's divided by your total mass. M is again total mass of the system. So same kind of thing now, except they don't. These are the locations are not along a line; they're scattered throughout a plane. But you still treat the moments the same way. Okay, the moment of a system of masses in a plane can be taken about any horizontal or vertical line. It doesn't have to be the x and y axis. Okay, in general, the moment about a line is the sum of the product of the masses and the directed distances from the points to the line. So, if you're using the horizontal line y is equal to b and the vertical line x equal a, then your moment about the horizontal line would be, because that's y is equal to b, would be m1 times y1 minus b plus m2 y2 minus b plus m3 all the way plus mn yn minus b. Minus b in parentheses, by the way. And the moment about the vertical line x equal a would be m sub 1 x sub 1 minus a. Now remember, this a's and b's could either be positive or negative. They still fit in here. If they happen to be negative, then this would be a minus and minus would be plus. But the formula is the same for the positive and negative. And there would be your moment about that vertical line or about that horizontal line. Okay. This would be your, I don't know if they don't have the, I guess you'd call this x bar sub a or something like that to indicate what you're with respect to. So here's example 3. Find the center of mass of a system of point masses. M1 is 6, M2 is 3, M3 is 2, and M4 is 9. Okay? Located at 3 minus 2 must be, 3 minus 2 is your M1. 0, 0 is your M2. Negative 5, 3 is your M sub 3. And 4, 2 is your M4. Now, either it's an optical illusion, or it looks like to me these here are bigger than those there. Those points should be the same. The outer circle represents the mass. This is 2, that's 3, that's 6, and that's 9. But it seems like, and maybe they are, but it sure looks smaller than that, and much smaller than that, the inner one. I won't get into that. I guess they're giving relative because maybe the 9 would be too big, so they made the inner part small. I don't know. But anyway, that's what the size of that corresponds, of the outer circle corresponds to the mass, as well as I can tell. Okay? Now, what does it say? Find the center of mass of the system of point masses. Okay? So let's do X bar. Now, do you want to do it in pieces or you want to do it all at once? You want to do pieces? Okay. I was afraid you'd say that. If you do it in pieces, and maybe we're thinking of different things for pieces, what would you do first? Yeah, okay. If that's what you're, now which moment you want to go for first? For some reason my pen hasn't come back. Okay, there it is. Okay, but we got two moments. This is a two-dimensional system, so we have an M sub x and an M sub y. Which one do we want to go for first? M sub x, okay. So if we're doing M sub x, then we're doing what? M1 times Y1, okay, plus, continue, M2 times plus Y3 plus, okay. I don't know why I started putting parentheses there. I don't need them, so I'm going to take them out. They just are in the way. Okay, so let's put in the numbers. M1 is 6 times, and what's your Y1? Help me, somebody. -2, I think I heard you say. Plus M2 is 3 times 0. I like that one. Plus M3 is 3. Plus M4 is 2. Okay. So the moment about the x-axis is do the math, it's easy. Pretty easy. -12 pretty easy. 6 plus 18 equal 12, right? This is 6 more and 6 is 12. Okay? Now, what you want to do next? You want to do the pieces? Let's do the pieces. Okay, well, let's do the moment of y. M sub y. Can we just write it down, or do I need to write the formula? Okay, so tell me what it is. 6 times 3 plus 3 times 0. I got that one. Plus. Okay, and that would equal. Help me, folks. Okay, 18 minus 10 plus 36. 18 and 36 is 54 minus 10 would be 44. Okay. What else do we need? Second? Total mass. What is your M? That's pretty easy. Help me. Okay. And that I think is 20, isn't it? 9 and 9 is 18 and 2 is 20. Okay? So, to get the center of mass, what do I need?
The X bar.
X bar and Y bar. What is your X bar?
It's MY.
M sub Y over M, which in our case is 44 over 20, which is 2.2. Okay. And your Y bar would be mx over m, and that would be 12 over 20, which would be 3/5, or 0.6. Okay? Now let's just see, for instance, how things look now. If you move this to 2.2 here, it would be about there, and then moved up 0.6 about there, does it look like you're kind of in the center of things? Your little masses are way to the left, and your big masses are close in to the right. That looks okay. Your above and below, you've got a really big mass a short distance above, and a smaller mass a little bit further above, and then you've got a fairly small mass slightly below, and then a medium mass slightly below too. I could buy that. So in other words, if you took your finger and put it under a massless plate that was holding all these things have those masses. You put your finger right there, it would be exactly balanced. Every state. So that's your center of mass. X bar, Y bar. And how we usually refer to it is an ordered pair, 2.2, comma, 0.6.
So the Y value would be?
Your Y bar is, they did 11/5, 3/5, which is the same thing. Why, I'm not sure, but yeah, either way will be fine. 11/5 and 3/5. So, easier to figure out where to do it on the plot, but okay. All right, make sense? Now, what you did was perfectly correct, did it by the numbers, exactly right. When I said, can we just do it straightforwardly? Here's what I was meaning. Now, remember your answer here, okay? But to me, this X bar would be M1x1 plus M2x2 plus M3x3 plus M4x4 over M1 plus M2 plus M3. Yeah, just do it that way. And that way, it kind of looks like, and indeed it is, that your masses are not canceling out, but it looks like they are. The units are for sure, and you wind up with an X thing. And that, to me, is easier than doing the MXs and MYs and all that stuff. Books, and probably your engineering instructors are going, or professors are going to want you to do it that way, and it's fine, do it that way. But to me, this makes visually more sense. That's why I said just do it. Because this is your M sub Y, and that's your M, and that's exactly what we did. But why go through all that? Well, just do it to begin with.
So that's M sub X over M sub Y?
And the M, say again? If you, no, okay, yeah, this is M sub Y, yeah. M sub Y divided by M is your X bar. And to me, that seems awkward because it's sub Y, but you're doing the X. If you do it this way, it makes, to me, sense, and And it's just maybe my weird way of thinking.
Do you have another example we can do that with?
We'll see. But Y bar would be IMSA 1 Y1, but yeah, it's the same type deal. Okay, but anyway, we got the same. Well, let's see. Let's see how they did it. I bet you they did it the way you did it, not the way I was suggesting. Well, they first write down the mass. They did that first. Not a bad idea. That's the easiest thing to calculate. They got 20, just like we did. Then they did the M sub Y, which is M times X, 1. Yeah, I like that. Just like you did, got 44. M sub X was 12. And then your X bar was M sub Y over M, which is exactly what we got. And M sub Y was 3/5. M sub X was that. Center of mass was 11/5, 3/5. Okay? Now, any questions on that before we move on? So it doesn't look like they're giving you another example now, but you can find them in the text if you want. I know there'll be some for homework exercises. If you have difficulty with them, we'll do them. But give them a shot. Now we're going to talk about the center of mass of a planar lamina. Okay? Now, planar, hopefully that makes sense. It's something in a plane, whatever that plane is. Okay? Lamina is a new word, and it's a pretty simple word. Consider a thin, flat plate of the material of constant density. There's the key, constant density, called a planar lamina. Thin, flat plate, that means it's in a plane. Constant density, that makes it a lamina. Okay? Density is a measure of the mass per unit volume. That's what density is. Such as grams per cubic centimeters, kilograms per cubic meter, pounds per cubic foot, anything such as that. For planar laminas, however, the density is considered to be a measure of mass per unit area. Because if it's a thin, flat plate, you really don't worry much about the thickness of the plate. You're only concerned with the area. Because if it's lamina, it's uniform thickness, uniform density. Okay. So then we talk about a density being a measure of mass per unit area. Or later we'll do pounds per unit area. The density is denoted by the symbol rho. That's not a P. There's no serif at the top here. It's a rho. It's the Greek lowercase letter corresponding to our R. I don't know why they chose that, but that's what they chose for density. Okay? The Greek letter, lowercase Greek letter, rho. Okay? Now, if you have a thin, flat plate of uniform density, if it's symmetric, then whatever its center is will be its center of mass. That could be a circle, it could be a square, it could be a rectangle, it could be an ellipse. The center will be the center of mass. You can think of the center of mass, X bar, Y bar, of a lamina as the balancing point, which is exactly what it was with all the things we were just doing. For a circular lamina, the center of mass would be the center of the circle. For a rectangular lamina, the center of mass would be the center of the rectangle, which were the two diagonals cross. Okay, that could even be true for a parallelogram, where the two diagonals cross. It doesn't even have to be a rectangle. Like I said, that could be an ellipse. It's where the major and the minor axis cross the center. Okay. Consider an irregularly shaped planar lamina of uniform density rho, bounded by the graphs of y is equal to f of x, that's up here, y is equal to g of x down here, and you're going from x equal a to x equal b. Now, this example they've made a and b both positive. That's fine. You don't have to, but it could be. Now, they have f and g both positive. You didn't have to. They could be down here, 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 anywhere. Okay? Across, anything like that. Okay? Shown here. the mass of that region, the total mass, is the density, which is uniform, constant, rho, okay, times the area. What's the area of this? We did that several sections ago, didn't we? It's the summation of all your little rectangles here, the x's here, as you go from the height of that rectangle is f minus g, okay? The width of the rectangle is your delta x or dx, and if you sum all those from a to b, do the integral, that's what you get. That's your area, multiply it times your density, that is your mass. So that's a fairly simple thing to go. Rho times the integral from a to b of your alpha of x minus g of x, that's the height, minus your thickness, which is your dx. As you go from a to b, here's your area times the density, here's your mass. This is mass per unit area times area. A is the area of the region. Okay. To find the center of mass of the lamina, you partition the interval a to b into n subintervals of equal width delta x. Equal width delta x. So b minus a divided by n. That's going to be what delta x is. Let x of I be the center of the ith subinterval. Okay? The ith subinterval somewhere out there, x of I is the center of it. You can approximate the portion of the lamina lying in the ith subinterval by a rectangle whose height is alpha of x of I minus g sub x of I, just like we did before, that's the height. Because the density of the rectangle is rho, then the mass is, of that rectangle, is m sub I, would be rho times the difference here times your delta x, which we were talking about before. Okay, so all this is making sense. Now, considering that mass to be located at the center, x of I, y sub I, okay, of the rectangle, the directed distance from the x-axis to x of I and y sub I is y sub I, which is simply the average of those two. If your alpha of x of I is up here, your g of x of I is down here, the midpoint is add those together and divide by 2. So the moment m sub I, okay, now this is little m moment, m sub I, not the total capital M, little m sub I about the x-axis is the mass, which is rho times the difference between these two times your thickness times your y sub I is the average of those two. Okay? Now, if you look at that very carefully, you'll see this times this, that's the difference times the sum of the same two numbers. So this is f sub x of I squared minus g sub x of I squared. So it's rho times that over 2, divided by 2, rho over 2, divided by L sub x of I squared minus g sub x of I squared times the dx. Sorry. Did I tell y'all before I went to the UAB football game on Saturday, and that's why my voice is like this.
I did too.
Huh?
I did too.
You did? Yeah. It was a good game, wasn't it? Yeah, it was amazing. It really looked good. Both offense and defense looked pretty good. Okay, moments and center of mass of a planar lamina if alpha and g are continuous functions. So the alpha of x, remember, it's all that's required. Alpha of x always be less than, greater than, or equal to g of x. Always. They can't do this kind of number. They can touch, but they can't cross. Okay? So alpha of x is always greater than or equal to g of x on the interval a to b. And consider the planar lamina of uniform density rho bounded by the graphs of y is equal to f of x on top, g of x on the bottom, a to the left, b to the right on x. The moments about the x and y axes are the moment about the x-axis is going to be the y. So here's your average y, rho times the average y, times the difference between the height, basically, of that strip times the thickness of the strip. M sub y, okay, that's even easier. Your rho, and what is your M sub y? Distance from the y-axis. That's your x. You don't have to do any averaging there. You had to average this to get this one. This is just x here. Then this is your height times your, so this is your area. Okay? So this is the easy one. This one's just a little bit more involved. The center of mass, x bar, y bar, is given by x bar is your M sub y over M, and x bar, y bar is your M sub x over M. Okay? M here is the rho times the integral from a to b of height times the width. That's the area times the density. Okay? Because this is the uniform density. That's the mass, total mass. So I think everything's done for you then. So if you take a look at these integrals here, again, like we saw before, this is the easiest one to do. The M sub y is the next easiest. You just multiply x by this. And the M sub x is just like it, except rather than x, you use the average y. The average y is f of x plus g of x divided by 2. Now, when you go to divide, notice your rows always go out. Yes?
Why is the my not a dy function?
Okay, good question. Because we express the change of y in terms of x's. Because we weren't given the functions in terms of y. So we did, it's a lot like the shell method versus the disk method. This is the one that works best here. This is stick with your dx's. Because everything is given in x. If they gave it in terms of y, then by all means do y. And then these two flip. This will be a y up here, and this will be a, let's call it h of y plus k of y divided by 2. So then you would do it that way. So, and then everything would be dy's, including this. If those two functions were functions like this, functions of y rather than x. Good question. Okay. I feel like I've been talking for an hour. What do we got? Yeah, we've got about 20, 25 minutes, something like that. Okay. Find the center of mass of the lamina of uniform density rho bounded by the graph f of x is equal to 4 minus x squared and the x-axis. So g of x is x, y is equal to 0. Okay? Very simple. Okay? Center of mass of the lamina, uniform density, rho, bounded by that. So what you want to do first? A little louder. We might. I can't hear.
Do we know our masses yet?
No, you want to determine that first? Sounds like a good idea. Your M. What is it going to be? Density times area, right? Density is mass per unit area. Multiply that by the area, you got the mass, right? Okay? Well, rho is a constant. A, however, is not a constant. So A can be expressed as an integral. I guess we need to draw a picture though, don't we? Okay. What does that look like?
It's a parabola going down.
Okay, parabola going down. You're right. So again,
It starts at 4.
1, 2, 3, 4.
What is A?
What's that? That's what we're doing now. The picture's going to help, I hope. What are some other points on it? Huh?
0 to 2.
0, 2. That's going to be where it crosses there, and, or not 0, 2, 2, 0 is what you meant to say, right? Maybe not.
The interval, is it going to be from 0 to 2? For the interval? Across the x-axis.
Okay. The x-axis is this down here. This is a parabola that does like this, right? So here's what we're at the center of mass of the lamina of uniform density bounded by this graph and the x-axis. So we're talking about this in here, right? Because 2, 0, when you plug a 2 in here, you get 4 minus 4. And minus 2, you get 4 minus 4. So that's where your y is 0. So this is the lamina we're talking about. So we've got to find the mass of this. Now, what I was thinking I heard you say is we can double that and go 0 to 2. Is that what you were meaning? Oh, of course you were. Okay, good. Okay, that's what I thought. Okay, double it because this is exactly the same on either side. I don't draw it that way, but it is. And it's uniform density, so it doesn't matter there. So what is the area over here? What's the height of that bar? Alpha of x. So that'll be 4 minus x squared. And the thickness of the bar? Width of the bar? dx. That's it. That's going to be, you double it going from 0 to 2, and you've got it knocked. Okay, so let's do this. This is 2 rho. Say again? 4x.
Minus x to the third over 3.
Okay, evaluate it from 0 to 2. All right, that'll be 2 rho times, pretty easy, 8 minus 8 thirds, which would be wouldn't it be, okay, 2 rho, okay, what'd you say? Oh, okay, I got it. 24 minus 8 over 3. Is that what you're saying? Yeah. And that would be 2 rho times 16 thirds, which would be 32 thirds rho. Yay? Yay. All right. Did too much of that Saturday. Okay.
What do we get the x cubed over 3?
What's that?
What do we get the x cubed over 3?
Okay. You're integrating x squared. Antiderivative of x squared. That's a power rule. Bump it up by 1, divide by that. N plus 1. Remember? How do we get the x to the first here? I mean, yeah, x to the first. This is times x to the 0th power. Bump that up by 1, divide by 1. Okay. All right, so there's our mass. That was the easy part. What you want to do next? Okay, that's usually the next easiest, m sub y. You remember what it happens to be?
Rho times the definite integral a to b, which in our case.
Okay, in this case, I think for right now, let's stick with minus 2 to 2. We don't know that we can double. You could on the mass. I'm not sure you can here. So let's see. What goes next? X.
F of x minus g.
Yep. That's it. So this will be rho, integral from minus 2 to 2. Multiply that through first, and what you get? X, and now do the integral. It'll be rho.
What about now find the integration?
Right.
Okay, so we have
2x squared, perfect.
minus full x to the fourth divided by 4.
Got it. Evaluated from minus 2 to 2. Okay. It'll be rho times. Put a 2 in there. What do you get? 8. Seems like we've had that before. Minus. Okay. Yeah, 2 to the fourth is 16 divided by 4 would be 4. But then we got a minus 2, not a 0, so we got to do it again. Minus 8. Then minus a minus is going to be a plus. This isn't going well, is it? Do we need to do this? Yes, it will be 0. Does that make any sense? They're exactly equivalent on either side, so the x coordinate has to be 0 because it's the same on either side. So we could have done that by observation.
Oh, this is a parabola.
It's a parabola, it's symmetric. Yeah, you did all that? All right. But you proved it to yourself now, haven't you? Okay. That was my. Okay. Can we do m sub x, or can I erase the m sub y since that gave us just a 0? Can I? Okay, going to erase that. The row's going to be the same. Those are going to be the same. This is going to be the only thing that's different. So from there on out, okay. What's going to be different about it here?
It would be 4 minus x squared
Over 2. Oh, okay, right. Yeah, 4 minus x squared over 2 here. Right. Because it's the height plus the bottom, which is 0, divided by 2. So, here we can pull the over 2 out, and then we have 4 minus x times 4 minus x, which would be what? Help me, somebody.
x to the 4th.
Okay, let's start with the 16, right? Okay, we can do x to the 4th if you want to do that. X to the 4th.
Plus 16.
Okay, we can do the plus 16. Is there anything else? When you square a binomial, it's the first squared twice the product of the two plus the last squared. you got the first and last squared, you didn't do the twice the product. You'd have a minus 4x squared and another minus 4x squared, which is minus 8x squared, right? So yeah, you can mix up the terms like this if you want to, if that's how you see it better. And if we're integrating that, what do we get? Got it? Plus 16x, got it? Over 3, right?
Is this the second part of the equation?
What's that?
Is this the second part of the equation, center of mass, or is this the...
I didn't put the x here. M sub x. Buy that or not?
No, because didn't we do M sub x earlier?
No, we did M sub y before. Okay, the x bar is coming out of the M sub y. Remember, they're backwards. Okay, this is where your y bar is coming from, the M sub x.
Okay, so we did the math and then we did the M sub y.
Yeah, we did M sub y, and that came out 0. Now we're doing M sub x, which will not be 0. Okay, I'll guarantee that one. So what do we get? Rows on the outside. $32 over 5.
Minus 64 over 3.
Okay. All right, you're rearranging the order again on me. Okay. Okay, yeah, minus 64 over 3. Plus 32. I'm going to have to extend my thing here a little bit. Okay. Then we're going to have a minus. Second. I can't. Yes, it will turn into a plus. I was just going to ask that. Minus a minus is a plus. It'll be another 32/5, right? And then we'll have a minus, a minus, a minus. So that will stay a minus 64 thirds again, right?
Plus 32.
Okay, and then another plus 32. Okay. Now, if you'll notice here, this one we could have doubled again. Yes?
What happened to the p divided by 2?
You're right. I was carrying things down and I forgot to. Okay.
We divided p by 2 because we didn't want to do 4 minus x cubed divided by 2.
No, this was 4 minus x divided by 2. And since that's just a constant, I pulled it out here. But then I forgot to pull it out in the other places because I just brought those down from before. But what I'm saying here, if you'll notice, we could have done, because our y's are the midpoints here, summing all these up, here and here, we could have just doubled it and gone from 0 to 2 again. That's exactly what this is doing.
How?
Well, you see, this is the same as that.
Okay, so the y is at 4, so
Yeah.
we could have done,
See,
so we could have done at 2, then double, and then cut it in
Yeah.
half.
Right. Yeah. Wasn't intuitively obvious that way, but it's indeed true. We could have done that. You can see here, that's exactly what we're doing. Okay? So actually, if you don't mind, I will wipe out the 2 here and wipe out half of those. Is that okay? So, let's just do that. And this is a real, now, the hard part of this problem is not the algebra, it's not the calculus, It's the arithmetic. It's adding fractions, okay? Least common denominator here is 15. So 3 times 32 is 96 fifteenths. I hope I did it right. 5 times 69, is what?
It's 64, not 69.
Oh, I can't read. Okay, 64, you're right. So 5 times 64, that'll be a little easier.
It's
320
320.
over 15. And then plus 15 times 32. Someone do that on the calculator for me. 480 fifteenths. Add the positives and you get 576 minus 320 is 256 fifteenths.
What was that last thing? Can you erase them? Can you erase them?
Okay. Is that enough erasure or you need something else?
I don't want to know what the last step is.
I did it in my head, is that right?
Yeah, that's right. No, I mean the multiplication that you were speaking of.
Okay. A little louder, I didn't catch.
The multiplication that you did at the end, you said 15 times 30.
Oh, okay.
5 times.
The least common denominator is 15. So I multiply this one by 3 to get 15. Multiply these by 5 to get 15. Multiply this by 15 to get 15. And then I added the positives and subtracted the negatives. And my nose itches, I must be going to have company. All this is times, times rho.
256 over 15 times
Rho.
P.
Times rho. Rho.
Do we divide by, do we do the 2? We have a,
Yeah, when I took out the 2 when I took out half of those. See, this is just doubling that. So rather than double that, I divided by 2. I'm just really lazy. Okay, sorry about that. No, I'm not. Okay. All right. Okay. Now,
so now you can take that and divide it by 32 row 3.
you got it. Okay? So we already know what your X bar is. 0. Okay? I've already erased enough of my graph, but you know that. Your Y bar is now this M sub X, which came out to be your 256 over 15 rho, divided by your M, which came out 32 over 3 rho. And notice what happens to the rows. You row your boat and they're gone, okay? So they're gone. So let's see if we can do this. 3 will go into 15 5 times, and 32 will go into 256 8 times. So you have 8 fifths is your Y bar. Okay, 8 fifths would be 1 3/5. So that would be right about there, would be your Y bar. And that kind of makes sense. You've got more mass at the bottom of this thing than you do at the top, so it'll be less than half the way up, but not a super a lot more. So 8 fifths, which would be 1 3/5. Just a little over 1 wait. Whoa, I did it wrong. I put 2 1/2. I don't have my thing there to see by. No, I did it right. That was right. 1 3/5. Okay, say again. Okay, I still didn't hear. Say again.
I got my book, they just put a dot. But for some reason they put a rectangle around that dot.
In the book.
Example 4.
Okay.
So I have of y it'll be 1.6, which is really close to 2. But with the X bar
X bar is 0, right?
Yeah, but here they have it like at -1. I don't get what the book's trying to do.
Okay. Let's, can I erase my scratch? We got what my answer is.
Oh, yeah.
Okay, it's, okay. And it is the same thing the book got, so let me erase my ink. Okay. Solution center mass lies on the axis of symmetry, which is X bar equals 0. Notice how fast they did that one. Okay. All right. Moreover, the mass of the lamina is that, which is exactly what we did, which came out being that, which is exactly what we did. We did it, 2 of them, we did it better than they did. Okay. And it came out 32 rho over 3. Remember, that's what we got. Okay. So let's now focus on the Y bar. Now this is what you're talking about, right?
Yeah.
Okay. What this dot is the midpoint of that bar, which is the center of mass of that bar, right?
Why do they have it at -1?
Second,
Why do they have it at -1?
they just picked it to be over here. They could have picked it to be right there, or here, or here, or here. They just picked it to be here. This is just a representative bar. Okay? And why they chose -1, there's no reason they could have. I would have left off everything here and just put a bar there, and it didn't matter what the X was. Okay? So the center of mass of this is going to be your halfway up it because it's laminar. It's uniform density. So there's your X, the Y bar for this thing, not like the Y bar. The Y center of mass for that bar would be right in the middle. Okay? Middle this way, middle this way. Okay? And that's where you got your F of X over 2. Now we took the over 2 and put it with the rho. But that's where the F of X came from. And there is your F of X. Now, that's the
We put the halves outside of the
right. We took this half and put it outside of the road too.
So
that's where we got F of X times F of X. Because this is your center of mass of it is there, of that bar. But the height is the whole F of X. So we got F of X over 2 times F of X. We pull the over 2 out with the row and just have F of X times F of X. And that's what we put it at.
could we have taken out the halves if we changed the indefinite integral to 0 to 2?
No, well,
No.
yeah.
Yeah.
Okay. Yeah, that's what we would have done. We would have, if we had just done 0 to 2, then the 2 we wiped out that half. You're absolutely right. And it would have just been the integral of F of X squared. You're absolutely right. Okay? The distance from the x-axis to the center of the rectangle is exactly halfway up, and the mass of the representative rectangle was that, which they have already talked about before, rho times F of X times delta X. So that would have given you, this is just like we did, except I pulled this out here, and what you're suggesting is go 0 to 2, which will wipe out that, and just have that thing squared. That's what we wound up with. See, there they pulled it out. They pulled out the 2 there, and that's exactly what we did, and got exactly the same values there, and that gave us 256 rho over 15, and then divide that by 32 rho over 3, and you get 8/5, which is how far up we got. All right, I think we're out of time, big time, aren't we? Okay. Homework exercises here. We'll begin next time with example 4. Well, we are on example 4.
We finished example 4.
Okay. Oh, they just show it if you put a balancing point there. That's the thing. That's a completely different graph. If you put it right there, everything would balance. That's all they're doing there. All right. Center of mass of a plane lamina. This is the bottom of page 499. Is where we'll begin next time. Okay. So, homework exercises here include, we made good progress, either 5 or 7, they're both at Calc Chat, 7's at Calc View, number 9's at Calc Chat, 11 or 13, both at Calc Chat, 11's at Calc View. Any of the odds, 15 to 27, they're all at Calc Chat, 15's at Calc View, and stop there, we'll pick up the rest of them next time. All right, good deal.
Hey,
Hey.